Just a reminder, there will be no class on Friday. I generally do field work over spring break and have to travel all the way to Texas to do it, so giving myself an extra day allows me to actually get it done. Um, all right, it's time. So we've been going through analysis of variance, which is one of the most used techniques in statistics. We finished up last time talking about the different assumptions that are involved in an analysis of variance. As I said before, these are really nothing new. We've seen these over and over and over again as we've gone through class. We were talking last time about how to test normality when we have an ANOVA, and we talked about how oftentimes in an ANOVA you might have really small sample sizes, and as a result, doing a test of normality on a really small sample size, you might find that you don't have a difference between your sample and normality simply because you don't have the statistical power to detect that difference. And so one of the ways that you can get around this is by actually looking at the residuals across the entire data set and then testing that larger data set for normality. So do you have any questions, pardon me, any questions about how that works in terms of getting the residuals and then testing those residuals for normality? It's just the Shapiro test, just like we've done before. Ultimately, we're not going to test the Shapiro test using a handwritten, hand-calculated calculations, because with these larger and larger data sets, it's just easier to do it in R. So we're going to spend a little bit of time in R, but mainly so that I can demonstrate to you that something is the way I tell you it is. When we come back from spring break, we're going to step right into R, learning how to do an analysis of variance within R. So make sure that you've gone through those tutorials that I gave you the other week, so that you are up to speed and ready to go. So we'll deal in R a little bit today, but if you don't feel like booting up R and going through all that, the thing that I'm going to do is relatively simple, and you can follow along pretty easily, probably without actually coding it in. So the last two things that we have to do to kind of have a complete coverage of analysis of variance is testing for the last of these assumptions, and then testing for differences among the means after you find that there is a difference somewhere in your data set. Remember that an analysis of variance doesn't tell you which means are different, it just tells you if some means are different or not. And we have additional methods that we then have to apply to a data set if we're going to figure out which specific means differ from which other specific means. But first, let's finish with assumptions. So the homogeneity of variance is assumption. Um, can somebody remind me why this is an important assumption? Anybody? We've talked about this a number of times. Anybody want to try now? Why is everyone so steely quiet today? Yeah.
Is it because like you have to have samples where the variances are like are relatively similar? Otherwise, like it's not. Actually, no, I'm actually not sure exactly.
I think you were headed the right direction. Somebody help them out. Blaine.
I think did you say that like it has to be like relatively similar to say that they came from the same sample or from the same population?
Not quite. If you're trying to make a decision between two means, so here you have two distributions, and I've drawn the means, and you're trying to tell if one of these means is different from the other mean, what makes telling them apart, difficult versus easy under these conditions? Is it easy for you to conclude that these two means are different from one another if the distributions look like this? Why not? Somebody else. Remember that we tell means apart by inclusion in other populations or not. So does it look like this mean is a member of this population? Yeah, it does. It's pretty clear. Yeah, that mean could have come from that population. Could this mean have come from this population? No, probably not. It's also pretty clear that that's the case as well. So if the question that you're asking is, are two means different? If that question is really, are these two means drawn from the same underlying statistical population? When you have two samples that have widely different variances, it's sometimes difficult to make that decision because it might look like one mean could have come from the distribution of another mean, but then the other mean doesn't look like it could have come from the distribution of the first. And so one of the main reasons that the homogeneity of variances assumption is so important is that it reduces ambiguity in making decisions about whether things are different or not. And that ambiguity is not something that we can deal with very easily. The whole point of doing statistics is to take human judgment out of the equation to a certain degree. Now imagine that you have three means that are relatively distinctive, and you have one mean that is really variable. So now we're in the world of analysis of variance, where we're trying to see if multiple means simultaneously are different from one another or not. When we calculate the analysis of variance, remember that what we're doing is we are taking the variation due to treatment, and we're dividing it by the variation that is randomly within the sample. In this case, what is the variation within this sample like? Small or large? We have small variation. What's the variation like here? Small variation. What's the variation like here? What's the variation in this sample? It's really large, isn't it? So now we have, for calculating the sums of squares within, we have small variance plus small variance plus small variance plus large variance. Those things added up might end up making the sum squares within really, really big, when most of that bigness of that within sample variance is actually just due to this one sample. If this gets too big, then this gets too big and we can't see the differences between the means because the F statistic then gets too small that we can't say that that F statistic is significant anymore. But it isn't because there aren't differences among some of the means, it's because you have one population that has a lot of variance in it and three populations that have very little variance. That makes your overall within sample variance really big, which makes your F statistic really small. And so the other thing is not only does it reduce ambiguity, it can obscure differences that are actually there. In this case, you might get a non-significant overall analysis of variance simply because of the variance in this one sample. And that's ultimately not what you're looking for. You're looking to get an accurate view of whether or not these samples are different from one another, and you would conclude under normal circumstances that this is different from that, this is different from that, and that is different from that, and none of these are different from this. But because this one has such a large variance, it might hide that fact. Okay? So how do we go about testing for homogeneity of variances? We use a technique called Levine's test. Levine's test has a really complicated calculation for calculating what is called Levine's W. And you can go and you can look up this in a statistical textbook. But in reality, what a Levine's test does is a Levine's test essentially does an analysis of variance on the deviations within the data set. So in this case, we have 4 hosts. We worked this out last time. We went through this example last time we were in class. We have these 4 hosts. We have the sizes of ticks. We calculated the mean, and then we found that there's a difference among these different hosts in terms of the size of ticks. But what we also discovered is that some of them have fairly big differences in the variances, as indicated by the sum squares within. And so what we want to know is, are these variances different so that we can trust this final conclusion that there's a difference among the means somewhere inside of this? In this case, though, pardon me, the deviations are not the residuals. They're the deviations from the median of the sample, is how Levine's test. So you can remind me what the median is in a data set. Yeah.
Middle number, half data sets above and half below.
Okay, the middle number. So in this first data set, we have 380, 376, 360, 368, 372, 366, 374, and 382. 1, 2, 3, 4, 5, 6, 7, 8 So there isn't one value that is in the middle. So what you do is you go to the middle two values, and 368 and 372 divided by 2 is basically 370. So this is the median for this first. Well, is that right? Oh, yeah, they're supposed to be in order, aren't they? Thank you very much for that. So what's the lowest value here? 360. 366. So 360, 366. Oh, there's two 360s, aren't there? Wait, that's a, yeah, that's 360. There's one 360. 366 then is 368. Then the next one is 372. And the next one is 374. Do we have to do any more ordering than this? No, because we have the middle two. 372 and 374 is actually 373, which is actually what I'm now remembering is the median. So the median here is 373. So we can ask ourselves, how far is 380 from the median? It's 7 units away from the median. How far is 376 away from the median? It's 3 units. How far is 360? It's 13 units. 368 is 5 units. 372 is 1 unit. 366 is 7 units. 374 is 1 unit. And 382 is 9 units. Notice that I'm just looking at the absolute value of the difference between the median and the values. And we could do this for each one of these. We could order the samples from highest to lowest. We could find the median, and then we could calculate these deviations. And what we would find is that we would find a table of deviations that looks like this. Are we right? 7, 3, 13, 5, 1, 7, 1, and 9. So this is a table of deviations of the mean from the, of the value from the median. And I'm going to argue that if we do an analysis of variance on this, we will get the same result that we would get if we were doing a Levine's test. So we could add all these up. This sums to 46, this sums to 96, this sums to 95, this sums to 76. You divide by the sample size for each of these, and you get the average deviation. The average deviation is 5.75, 9.6, 7.31, 12.67. We can get the variation within the sample the same way we would do for an Anova: 119, 360, 376, 282, and 333. Once again, these are all weighted. They're not weighted, rather. Forget that. They're not weighted by the means. You add all these up to get the sum squares within. We have the overall average deviation for the entire data set. And that then is used to calculate the sums of squares among. Once again, each of these is weighted by the size of the data, the sample size for each of the samples. So we now have sums of squares within, we have sum squares among, we have sum squares total. We can fill out our table, and we find an F statistic of 1.93. And when we test that, when we look that up in Daniel Soper's website or whatever, we get a p-value of 0.143. We would conclude that the variances are not different. So we can calculate a Levine's test. It's the same technique that we used before for doing an ANOVA on the raw data. One book that I was reading, it says, it's weird that you do an ANOVA on the deviations to find out if you can do an ANOVA on the data itself. So usually when I tell students that this is what Levine's test is, they look at me like I'm crazy. So let's go to R. If you want, follow along at home. I'm going to clean up my data frame here. So the first thing that you want to do is check and see that you're in the right directory. My directory is the rscript directory on my computer. Make this bigger so you can see it. If it's not the correct directory, then obviously you need to get there. The tix.csv folder or file is the data set, and you can see that I have the host, which I have recoded with letters rather than numbers, simply so that R will recognize it as factor data or character data straight up. You have the carapace length, and then I've actually put in the deviations from the medians. So I went in and figured out what the median was for each of these treatments, and then calculated the deviation of the value from the median. If you want, you can also look at the whole data set, and you can see that I have done that for the whole data set, all the way down through the fourth one. So we have a column of deviations and we have a column of carapace lengths. So we need a couple of packages. Like always, it's nice to have ggplot2, rmisc, and particularly in this case, we need car. Car is the package that has Levine's test in it. So if you're ever going to do a Levine's test, you need to have that package available. I've got some things in here for formatting, but we're not going to be making any graphs. I can ask it for the class of the host. Remember, I told you class is one of the things that I use a lot. It's character data, which is what we want the host to be, and the carapace length is integer, which is also what we want it to be. So R is paying attention to the data the way we want it to pay attention to the data. So we can check for the normality of the data. Oh man, I deleted some stuff while I was messing around with this earlier. So how do we check for the normality of the data? Yeah.
Shapiro test?
We use the Shapiro test, but what is going to be the data input for the Shapiro test? It's going to be the Shapiro test on the raw data. In this case, carapace length. We find that it's not significantly different from normal, but the p-value is kind of on the low side, and this might actually be because we might have multiple peaks, simply because we know that the analysis of variance is significant. What would we really want to be testing the Shapiro test on? Do we want to do it on the raw data, or do we want to do it on something else? Don't think about it from an R standpoint. Think about it from a statistical knowledge standpoint. What do we want to test residuals on, or test normality on? We want to test it on the residuals from the model, right? So in R, let's make an analysis. We'll just do analysis 1 is the analysis of variance, and it is done on the carapace lengths as they're determined by the host that they come from. And the data set that we are using for this is DAT in my case, because that's what I named my data set. And when we do that, you can get a summary of this. And what the summary should give you is it should give you an Anova table. And this Anova table should look exactly like this Anova table that we've already seen. An F statistic of 5.26 and a p-value of 0.00445. When we do it over here, we get an F value of 5.26, and actually the p-value from the PowerPoint is actually pulled from R. Sums of squares are 1808 and 3778. Sums of squares are 1808 and 3778 with a little bit of rounding. So it looks like we did the analysis of variance correctly, because when we did the same analysis of variance in R, it calculated the same Anova table that we calculated. Yeah.
So Levine's test is literally just running an ANOVA on the deviations from the median.
Deviations from the median. So we'll get there in a minute. So just hang with me for a minute. So one of the things that you can do is you can add another column to your data file that says that is where you're going to store your residuals. So dat $res is going to be where we're going to put the residuals. And so to get the residuals from something, you just ask it for residuals from whatever that something is. In this case, it's analysis 1. Analysis 1 is our ANOVA, and so this will just give us the residual values from the ANOVA. And we can head the data file to see that it did that. And once again, these residuals should be positive and negative in the right directions, et cetera, et cetera. So for our first, we can check this because for our first mean here, our first mean was 372.25, and 380 minus 372.25 actually ends up being 7.75. So our first residual should be 7.75. So once again, we can check to see that R is doing what we asked it to do. Now we can do a Shapiro test on that $res, and we will have a much stronger test because it has a bigger sample size, and it's less non-normal than it was before, primarily because by taking the residuals, we got rid of any non-normality that was due to the raw data just being distributed differently because it was in different treatments. So taking the residuals from the analysis and doing a Shapiro test on this larger data set oftentimes gives you a more satisfying answer as to what the normality of the data are. Now, analysis of variance is tricky because you can do analysis of variance a couple of ways. You can do analysis of variance using the analysis of variance command, but you can also do the analysis of variance using linear models, and it should give you the same answer. So here is me just redoing, let me change this now to analysis 2 here. This is linear model, but you specify it the same way. It's the response variable tilde the categorical variable, the treatment variable, and then the data. And when you run this, you can type in summary.aov in that analysis, and what it will give you is it will give you an Anova table. And this Anova table should look exactly like the Anova table before, and when you go and scroll up, it looks exactly like the Anova table you had before. So this is also really common in R. There are about a dozen ways to skin any analytical cat you want to skin. And if you have one way that you prefer versus another way you prefer, it doesn't really matter. If the people who wrote these packages and programs are doing their jobs correctly, they should all give you the same answer. It doesn't matter to me whether you use AOV or whether you use linear models. In reality, an analysis of variance is just a special case of linear models. So anything that you can analyze with the AOV package, you can also analyze with linear models. The reverse is not true, though. There are linear models that you cannot analyze with the AOV package because they're not strictly linear models. So, they're not strictly ANOVAs. So once again, just a couple of different ways of skinning the cat. Notice how since I was using linear models, I didn't just write summary like I did up here. I had to write summary AOV, summary.aov, and that's because I want it to give me the summary in an analysis of variance table. If you just type in summary, it gives you the same kind of information, but it is not necessarily in a way that's easy to extract the information. It still gives you the F statistic, it gives you the degrees of freedom, and it gives you the p-value, but it doesn't give you the stuff that is normally found in an Anova table. To get that, you have to put a .aov at the end of that, and then it'll give you the Anova table. So, the Levine's test, you could do a Levine's test on the linear model that relates carapace length to host, but that's not actually what we want to do. We want to look at the Levine's test. Well, actually, sorry, my bad. We do want to do the Levine's test on the raw values of the data as they're determined by host. And when we do that, we will get a Levine's test that gives us an F value of 1.9308 and a p-value of 0.1438. So these are the results of the Levine's test on the tick data. This is 3 and 33, just like the Anova is. Is that what we got when we calculated it by hand?
What does that mean, 3 and 33?
The degrees of freedom. 3 numerator degrees of freedom and 33 denominator degrees of freedom. So when we go over here and we look at the one that we calculated, when we calculated it based on the median values, the deviations from the median, we got an F of 1.93 and a p-value of 0.143. But of course, you didn't do these calculations. I did these calculations. I could just easily be lying to you. So let's go back to R and say, Dr. Kowinski told us that a Levine's test is simply an analysis of variance on these deviations from the median. So let's set up another analysis, analysis 3, and we're going to now do an analysis of variance not on the carapace lengths, but on the deviations as they are determined by the host from this same data file. If I have been honest with you, when we run this line, it should give us the same thing that we see in the PowerPoint, and it should give us the same thing as the Levine's test that is in the Levine's test output that we just generated. So we run that, we get a summary of that, and what we get is 1.931 and 0.144. Same, 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 same. Same degrees of freedom, same everything. A Levine's test is just an analysis of variance on deviations from the median for each of the samples. That's all a Levine's test is. One of the nice things about statistics is there's a limited number of bags of tricks. Sums of squares, it's a limited bag of tricks. Sums of squares we're going to use to analyze analysis of variance. Sums of squares we're going to use to analyze regressions. Sums of squares we're going to use for analyzing analysis of covariance. Statisticians don't have that many tricks up their sleeves. Anova, one trick. It's a trick that is used for seeing if means are different from one another. It is also a trick for seeing if variances are different from one another. One trick. There are a limited number of tricks in statistics. Learn them, and the world will be the path to your door. Questions? Yeah.
So, with the Levine's test, we're running an analysis of variances on the deviations from the median.
Mm-hmm.
Our entire goal is to see whether there is in fact homogeneity of variances.
Yes, because if homogeneity of variance is not met, if the data are what is known in the biz as heteroscedastic, you're about to go home for spring break. If your parents ask you what you're learning at Jewel, say, well, I learned what heteroscedasticity is. Heteroscedasticity is simply fancy pants name for the variances are not similar to one another. Right. One of these variances is not like the other. If this is violated, you're dead in the water in terms of this analysis because of the reasons that we discussed at the beginning of class.
And our p-value for the Levine's test needs to be
above 0.05.
Above 0.05?
Above, you're looking for it to be above 0.05 because you don't want to see differences. Differences would be indicated by a p-value below 0.05.
We want no differences.
You're looking for no differences, yeah. That's what you want to find. That's what you hope to find. Yep. Any other questions about Levine's test? If you can do an Anova, you can do a Levine's test. Now, you can do a Levine's test the hard way by figuring out the deviations from the median and making a separate column in your data file for that and everything else. Or you can just type in Levine test for whatever your model is. And in this case, I've written the model out, but you could just as easily, since I've already defined this as analysis 3, you could just as easily just type in analysis 3 and it will do it. Oh, crud, no, not analysis 3, never mind. This was analysis 1, wasn't it? Yeah, you could just as easily do it on analysis 1, and when you do that, it should give you the same thing that we had before. So you don't need to do all of that calculation of the deviations and all that. I did that just to illustrate this point. Questions? Okay, we've tested our assumptions. We have data that are normal. We have data that are not different in terms of their variances. We calculate the Anova, and we find in the Anova for this particular situation that the Anova is significant. But once again, that doesn't tell us anything about whether or not these means are different from one another. So we need a tool for doing that. So there are two ways of doing this. One way of doing this is using what we call planned comparisons. A lot of times we do an analysis of variance because we think that there are going to be some differences that we're interested in before we even go out and gather our data. And when we know this, it gives us more power to ask questions of our data. If we expect the control in the peas growth experiment, if we expect the control to have higher growth than all the other sugar treatments, then we can actually plan to do that comparison. If we get an overall analysis of variance, we can do this planned comparison. And because we had this idea, what's known as a priori, before the fact, we can do that comparison and we don't eat up our degrees of freedom or our alpha rate, our alpha level in the process of doing this. We might have another hypothesis that the double sugar sucrose is going to have higher growth than all of the single sugar groups. Once again, this is another comparison that we might have a priori simply because we know something about the way plants grow because I'm a botanist. I'm not a botanist, but a botanist had that idea. So these planned comparisons are things that you think about before you do your experiment. They're comparisons that you want to explore before you ever go and gather your data because you're doing this work for a particular reason. You have a particular goal in mind. Now, these things should be orthogonal. And orthogonal is just a fancy pants word for saying that they should be independent of one another. And the way we do this is we do this by essentially controlling what we're comparing to what. And so if we have sucrose versus the 1-to-1 mixture of glucose and fructose versus the 2% glucose versus the 2% fructose versus the control, we can basically define what we're doing here by putting coefficients in front of these. And the coefficients basically define what's being compared to what. So we might want to compare the control to each of these other treatments. That's what this comparison is doing. We might actually want to compare the double sugar to all of the single sugar groups, in which case we would have the double sugar compared to the single sugar groups, and we would have no coefficient for the control because we don't really care what the control is in this case. These two things are independent because the structure of what we call contrast, these are called contrast coefficients, is different. In this case, we have two groups, which means we have 1 degree of freedom associated with this comparison. In this case, we have two groups, which means we have 1 degree of freedom for this comparison. But we might also want to compare among the single sugar groups. So what we want to do is we want to know, is the 1-to-1 glucose-fructose mix different from the 2% glucose, different from the 2% fructose? So we would have no coefficients here. We would have a -1 here, a 0, and a +1 here. This is now 3 groups. As a result, this takes up 2 degrees of freedom. So for each of these comparisons, we can know what we're comparing, and we know how many degrees of freedom they're using up. Yes?
Sorry, where are these coefficients coming from?
I'm just making them up based on what I'm wanting to compare to one another. So, yeah, and actually, sorry, I messed this up. These aren't zeros. This is -1 and -1. Oh yeah, that's complicated. Sorry, I wasn't thinking through how you write contrast coefficients because I haven't done this in a while. Contrast coefficients should all sum to 0. My bad. So this would actually be -4, 1, 2, 3, 4. This would be -3, 1, 2, 3. And this sums to 0 because you have a -1, a 0, and a 1. These are just coefficients that you use to tell R what you're telling it to compare to one another. It's basically setting up 3 different treatment variables. All of the sucrose is going to get coded 1. All of the glucose fructose is going to get coded 1. All of the glucose by itself is coded 1. All of the fructose is coded 1. And this is coded -4. So in this case, there were 10 observations for each of these, right? 10 observations. So in this case, we now have 2 groups. One group has 40 observations and one group has 10 observations. So it's just another way of kind of recoding the treatment levels, because now you're comparing the control to anything with sugar in it. You could have just as easily written this as control and sugar, 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 but the way we usually do this is with numbers. And the reason that we do this with numbers is it helps us keep things straight, because if these are all in one group, the number that defines this should be the opposite sign and the sum of all those things that we're comparing it to.
Okay, so they're kind of just arbitrary.
They're just arbitrary. We could have easily coded this -1, -1, -1, -1 +4. We could have coded it, this would make even less sense, 2, 2, 2, 2, and 8. It doesn't matter. It's just a way of telling the computer what you're doing. We typically work with pluses, +1, -1s, and zeros because they're just simpler to kind of think about. So in this case, if this is -1, -1, -1, -1, this would be +4. This is -1, 0, and +1 because it all sums to 0 and it defines 3 different groups. The 1-to-1 glucose fructose, the 2% fructose, and the 2% glucose. But notice that we are eating up degrees of freedom. So if we go back to this example here, we have 5 treatments, which means we have 4 degrees of freedom in the treatments. The thing about orthogonal contrast is you only get as many planned comparisons as you have degrees of freedom to do them with. You have 4 total degrees of freedom. You've now used up 1 degree of freedom, a second degree of freedom, and 2 more degrees of freedom. You're done. You've used all of the degrees of freedom that you have available to you. Now, you could do some other planned comparisons if you wanted to, but you would have to get rid of one of these planned comparisons in order to gain the degrees of freedom to do those. So one of the ways in which planned comparisons preserves your type 1 error rate is it doesn't let you go beyond the number of degrees of freedom that you have to work with. It places a limit on you. And you can actually ask R to do multiple planned comparisons that exceeds your degrees of freedom. But what it will do is it will do them in the order that you ask it to, and when it runs out of degrees of freedom, it will just stop. And it will send you an error message that says you have exceeded your degrees of freedom, and I'm not going to do this anymore. I see what you're trying to do. You're trying to game the system, and I'm not going to let you because I'm a unyielding machine. So planned comparisons are nice because you can test each of these things separately, and you can still rely on the type 1 error rate of 0.05 to test all of these different comparisons. There's no penalty for that. And there's no penalty for it because you were interested in these hypotheses, in these differences before you ever went out and gathered your data. And that's the fundamental difference. And that's different from unplanned comparisons, where your original question was, are there any differences, and you aren't really sure where those differences would lie or what direction those differences would be. You found some differences, and now you want to explore what those differences are. This is what unplanned comparisons are. And unplanned comparisons have less power than planned comparisons do because you're doing them after the fact. And you can only do this after you've done an initial ANOVA that showed that you had some differences that you want to go looking at. If you don't observe a significant ANOVA, you don't do unplanned comparisons. The weird thing is you can get a non-significant ANOVA and still do planned comparisons because it's basically subsetting your data. You had this general hypothesis about the whole experiment. You didn't find a result there, so now you want to look at some specific comparisons that you had before you even went into this, and those differences might be significant if you get rid of some of the variation that is due to some of the other treatments. And so in that way, planned comparisons are also different in that you don't need an overall ANOVA, significant ANOVA to do them. So in this particular example, once again, we're going back to the P data. We can't exceed the number of treatment degrees of freedom, which in this case is 4. So you could do control versus all of these guys. You could do these guys versus that one. You could do these 3s versus one another, but then that would be it. You could do this comparison, which has 2 groups, which has 1 degree of freedom, and then you still have 1 more degree of freedom that you could use for planned comparisons. So it all depends on what your questions are about the data as to how many different planned comparisons you can accomplish. So here we have the final ANOVA that we got from running this data set. We worked on this last week, I guess it was. So what we usually do for unplanned comparisons is we use this test called the Tukey-Kramer test. And basically, this is what we call a minimum significant difference test. And so what we're going to be trying to calculate is what is the minimum difference that can be between two means to say that those means are different. So MSD is the minimum significant difference, which is another way of saying what is the smallest difference among means that we would conclude as different. And the way you do this is you calculate the MSD, and it's just the critical value, which you look up in a table, times the standard error. And the formula for the standard error is just stuff that you already know, which is the mean squared within, because what is the mean squared within again? The mean squared within is just the sums of squares within divided by the degrees of freedom. It's the sample variance. Sample variance is then divided by the sample sizes of the two samples that you're comparing. In this case, they would all be 1 divided by 10, so it's 2 divided by 10, so it's 0.2. But this is just simply the sample variance divided by 2, and then you take the square root of that, and that gives you the standard error of the mean. The standard error, because this is, once again, the sample size in this case. You're comparing two means in this case. So for the p growth data, the critical value, so you can go to a book of statistical tables. The critical value for a chi-square test is Q. And so you can find a table of Q for your particular sample size. In this case, it would be the sample size of the two samples put together. And so Q is the number of treatments, which in this case are 2, and the number of degrees of freedom for the mean square within. For this case, it's 4.02. And if you calculate, if you go back to this situation here, the mean squared within for the two treatments that you are looking at would be, if you're comparing, for example, control to glucose, it would be 142.9 plus 24.10, and then you would multiply that times 0.2, and then divide that by 2, and then take the square root of that. And that's just basically what this is, and that's where we get this. Oh, I'm sorry. No, bad. I told you the wrong thing. Because this is the minimum significant difference value for everything. It's actually the total sum squares within. That's what it is. Not sum squares within, mean squared within. So 296.33 is the mean squared. No. Losing my mind. It's time for spring break, isn't it? Mean square within 5.46. So SE should be the square root of 5.46 times 1 over 10 plus 1 over 10, which is 2 over 10, which is 0.2. So 5.46 times 0.2 divided by 2, and take the square root of that. And if you do that, it should be whatever I have on the next slide. 0.7389 times 0.402 is 2.97. Yeah.
So is that like that's another way to calculate the actual standard error?
Just for this particular test.
Oh, okay.
Yeah, don't calculate standard error normally this way. So 2.97 is the difference. So any difference bigger than that is a significant difference. So what was the value? It was 2.97, 2.97. So what you do then is you ask yourself, well, what's the difference between the control and the 2% glucose? What's 10.8 units? What's the difference between control and fructose? 11.9. Control and the 1-to-1 mixture is 12.1. control and sucrose is 6. So 64.1 minus 70 is 6. So these are all the differences. And then above the line here, these are all of the minimum significant differences. Now, if you have different sample sizes for each of these pairs, these numbers will change because these two numbers will be different. But you shouldn't expect them to fluctuate a ton. In this case, they're all the same because we have a sample where all of our samples are 10 observations. So these are all the same. And so the question of which differences are significant is simply, is this number bigger than 2.97? Is this number bigger than 2.97? Is this number bigger than 2.97? This number is smaller than 2.97, so this is not a significant difference. 2% glucose is not different from 2% fructose. 2% glucose is not different from the 1-to-1 mixture. Glucose is different from sucrose. But of course, we already suspected this, right? Because somewhere back in the past, we made a graph of this where it looked like 2% glucose is not different from fructose or the 1-to-1 mixture, but it looked like all of these were different from sucrose, and all of these are different from the control. So when we go and look at our results from doing the Tukey's test, what we should find is we should find something that kind of comports with what we expected. The control is different from everybody else. The simple sugars, glucose not different from fructose, glucose not different from the 1-to-1, fructose not different from the 1-to-1. All three of those are not different from one another, exactly as we expected. And then when we look at sucrose, sucrose is different from the three simple sugars and is also different from the control. The Tukey's analysis should comport with what you find when you graph the data with their means and their 95% confidence intervals. Yes?
Sorry, how is this, like, so those are the means up top there?
Yeah, these are the means for each treatment, means of each treatment. Obviously, you don't compare control to control because that would be a mean of 0, or a difference of 0. So the difference between the control and the glucose added is 10.8.
Right, and then, but, sorry, it's like, why are there numbers on the other side of that table?
This is the number that you compare to.
Right.
And in this case, they're all the same because everybody is a sample size of 10. But imagine if you had one sample that was a sample size of 10 and you had another sample that was a sample size of 8, this number wouldn't be 2.97, it would be something different. So if glucose was a sample size of 10 and fructose was a sample size of 8, this value wouldn't be 2.97, it would be something else.
Right, but like, you don't have every comparison in this table, do you?
I do have every comparison.
Well,
Control to everybody, glucose to everybody, glucose to everybody except for control, which it's already been compared to, fructose to everybody except for control and glucose, which it's already been compared to. So this does represent all possible combinations. And above the diagonal, I've just put the critical value, the minimum significant difference, and below the value, I've actually put the actual differences between the means.
okay, thank you, I thought we
Yep.
had trouble reading the table.
Yep, that's perfectly expected. Yeah. Once again, it doesn't make a ton of sense because these are all the same number. But if you had different sample sizes, you would have a table with lots of different numbers. And so you just compare, this compares to that, that compares to that, that compares to that. This compares to that, that compares to that, that compares to that, et cetera, et cetera. So it's just a way of illustrating the differences. All right, questions? Most people don't have planned comparisons because most people don't think about their data very much before they actually go out and gather their data. The problem with unplanned comparisons is that This is a system that operates where it's attempting to control your overall experiment-wide type 1 error rate. So you're still testing everything at a 5% type 1 error rate, but because you're doing these comparisons after the fact, you have less power to see differences than if you did these as planned comparisons. And I remember in grad school sitting in a class where we were learning about this in a course on analysis of variance, and one of the graduate students asked what seemed to him a reasonable question, and the question was, well, couldn't you just do your test afterwards and call them planned comparisons even though you didn't have planned comparisons at the beginning and take advantage of the increased power to find differences? And a friend of mine named Mike Keck, he leaned over to the guy and said, well, yeah, you could just make up your data also. So whenever you're doing planned comparisons, know that there is an advantage to doing that in terms of the power to see differences. And if you didn't have those planned comparisons really before you went and gathered your data, do not test them with planned comparisons. It's kind of a form of gaming the system, cheating, if you will. If you really didn't have any expectations about what might be different from what, just use unplanned comparisons. Chances are you're going to see those differences anyway. But just as a matter of statistical propriety, if you didn't have the comparison planned before you started, then don't say it was planned before you started. It gives you a slight statistical advantage. You have two data sets now in your pocket. I've given you a small window into how to analyze these in R. Spend some time over spring break. I know what you really want to do is you want to just relax. Take the P data set and the tick data set and see if you can do an analysis of this using an analysis of variance. And couple of things that you want to do, and we're going to go through this in detail, so if you mess up and it doesn't work for you over spring break, don't worry, we're going to start live coding Monday after spring break. We're going to spend probably a week and a half in nothing but live coding after that. I will help you through the live coding of it, but things that you need to be able to do an analysis of variance is you need to be able to obviously read in your data. Would it be nice if you could visualize it so that when you test normality, you can look at a distribution of the data and verify for yourself whether or not those things look normal or not? Then you need to test for homogeneity variances. Which I showed you today. You also need to test for normality, which is the Shapiro test. This is Levine, lowercase Levine test. And then you have to do an analysis of variance. I've given you 2 ways today of doing this. And what I haven't given you today is I haven't given you the code for running a Tukey's test. But see if you can figure out Tukey on your own. And then, of course, the last thing that you might want to do is you might want to make a meaningful graphic. What do you need in order to make a meaningful graphic? What information do you need? You need axis labels, so you need what the x-axis is, what the y-axis is. What else do you need? Means? Yep, means.
I was saying means and their
95% confidence intervals. Do you know of a command in R that I've given you in the past that calculates all that for you? It's found in the package rmisc. Summary SE. Summary SE will give you a data frame that gives you the mean, the sample size, variance, standard deviation, and the confidence interval. And so you can use Summary SE to then figure out what gets plotted. And one of the things we haven't spent hardly any time in here at all on is graphics. So if you get this far, try and plot it. I usually use ggplot2. So see how far you get through this. So we'll see what you're capable of doing in R. If you don't get it done and you get stuck, feel free to email me. If you get stuck and you just don't want to mess with it, we're going to go through in live code every step of this starting on Monday. All right? Questions? Yeah.
Could you go back to the last slide for just...
This one? It's in the Anova thing that's on.
The bins are like manifest the individual
Sample 1 and sample 2.
sample size.
Sample size. They're small n, so that always refers to sample size. The big N refers to the entire experiment. And that's why this thing can change depending on what pair of things you're comparing to one another.
That's just
So
for a given comparison.
for a given comparison, yeah. So if you were doing this, so another way that you could practice this is go back to the original tick data. Comparing tick 1 to tick 2, host 1 to host 2, host 1 to host 2, you have 1 over 8 and 1 over 10. Comparing 2 to 3, you have 1 over 10 and 1 over 13. So that's why those values will change.
Sounds good.
Yep. All right. See you guys after spring break. Yes, ma'am. Yeah. What up?
So I got this from the Moodle site, and I was just trying to
Uh-huh.
go through it, and it has everything already. But when you do the Shapiro Test,
Mm-hmm.
is this supposed to be like the residuals?
Yeah, and so I actually was changing things as I was going.
Oh, okay.
So your residuals are saved differently. So what you can do is, this is asking for residuals just in a vector, essentially.
Okay.
So what you can do before this is just go in and make yourself a new vector called res. And res is essentially residuals of analysis 1. Okay, because you did analysis 1, that's the actual ANOVA.
Okay.
You want the residuals from that. What this is going to do now is it's going to put those. Whoa, what happened? Oh, it helps if I know how to spell. Do you always gasp when R gives you an error message?
No, because I get them all the time.
Okay, so there's just it's just an array of the residuals. It's actually a vector, and they're just showing it to you in wide format.
Okay.
So now when you do a Shapiro test on that, it should give you the 0.8503,
Okay.
which we saw when we did
Okay.
it. Yeah, I changed things up while I was going through it with you, so that parts of the code after that won't work because of the way that I did it. Because the way I did it and the way you did it also, maybe, or maybe didn't. Yeah, the way I did it was I actually stored, instead of taking the residuals and just making a vector out of them, I actually stored the residuals in the data file, which you can also do. And now res is still there because res is there, because you've already generated it. But now head that, and you should see there's a new column with the residuals in them. Okay? And you see how the residuals are slightly different from the deviations, and that's because the residual is how does this differ from the mean versus how does this differ from the median.
Okay.
Okay?
Thank you.
All right? Sure.
Okay.
Yeah.
I was here for the first 2-3 minutes of class. Did I just say housekeeping items or anything?
I don't think so. No class on Friday, and what else was there? Just the stuff that was written on the board when you walked in.
That's it?
Yep, I think so. Yep.
Unfortunately, I don't think on Athens anything that we use is still on R.
Okay. No computer. You don't have a computer?
I do.
No.
at home, but I don't know whether I would be home
Uh-huh. Well,
to right now.
do what you can. Like I said, we're going to live code this all together when we get back. I'm just kind of, I find it useful to encourage students to figure things out on their own. It sometimes just breaks down the mystique of R, like, ooh, R is this thing that I can't figure out. No, it's something you can figure out. You just need to be given the opportunity to figure some things out on your own. I will eventually spoon feed it to you, but my guess is if it's spoon fed to you, you learn it less well.
Fair enough. So you're
So-
saying go out, try it ourselves if we can.
Yeah. Yep.
Sounds good. Thank you, okay.